What is a function?
A function relates one or multiple values together. So you can have y equals x as a classic, f of x equals x.
It's a classic.
It's a classic. Yeah, I mean y equals x is the one everyone sees.
What about y equals 4?
Y equals 4, that can be a function
it's
as
a
well.
classic.
Yeah.
So it's a way to write a rule that connects two sets. One set is where those numbers are. You can think of them as random variables, but then random numbers. But then in the other one, those random numbers are connected to a specific one. So typically, a function is a mapping from one set to another by a rule. So if this set is called x, the function that takes values of this set transforms and creates another set, normally it's called y. Okay, so the rule that connects y to x is this function. Now, there is much more to that, but for us it's enough. So an example of a function could be y equals the classic one, I guess, x. Essentially, this set mirrors this other one. Y equals x to 3x plus 1. That's another one, and so forth. Okay? Yeah. In different fields, they call x the independent variable. And they call y, or the outcome of this function, the dependent variable. Okay? So what are the different types of functions that we might encounter here? The nicest of them is a linear function that kind of looks like this. You have y equals a number, x plus another number, where a and b are constant. Okay, so x is an independent variable, a is a fixed value, b is a fixed value, and you get something like this. Then you have a polynomial. And kind of looks like this. Y equals some number, x raised to a power, plus another number, x to lower power by 1 unit, and it continues like that. All the way to x, and then a constant. So we're an minus 1, all the way to 0 are constants. Yep. So an example could be 7 x to the 32nd plus negative 8 x to the 17th. So there's a bunch of other values of a at 0 in that case, and so forth. An example of this that you have encountered before could be 3x squared plus 5x minus 1. Yeah, so there is only how many terms?
3.
There's only 3 terms, right? Okay. But they could be as complicated as that. In real life, we actually use those. Have you ever used a thermocouple? So it's like a little probe to measure temperatures. There are 2 pieces of metal connected at one point, and those two pieces of different metals, where every time you put 2 pieces of metal together, they produce a tiny, tiny current. It's just a physical property of metals interacting with each other. And it turns out that the current is proportional to the temperature at which the connection of the two metals is. And the proportionality factor is a function that kind of looks like this, with like 14 different terms. And it works really, really well. Something like that can model that behavior, the connection between those two specific metals and temperature and current flow can be modeled very well by this. Surprised you haven't used a thermocouple. I mean, who wouldn't? The type of polynomial equations we're going to use here, they're mostly going to be either like that, a quadratic, or maybe a cubic. I think we're not going to go any past that. Next, you have rational equations. Rational function, not equations. A rational function is typically one polynomial equation divided by another polynomial equation. So I'm going to look like this. an x to the n plus an minus 1 x to the n minus 1, and it continues all the way to a constant, divided by another polynomial, b k x to the k plus bk minus 1 x to the k minus 1, right there. So these can have 7 terms, these might have 3, or vice versa, or whatever. They don't have to necessarily be of the same length. There is one problem with rational equations, and it could be there are some values of x could make the denominator, so the bottom of this fraction, equal to 0. So there could be values, specific numbers, that make this whole quantity equal to 0. What do you know about the fraction divided by 0?
It does not exist.
You cannot divide by 0, so there is an issue. So those functions at those points, they have some discontinuities. So those functions, when you're dividing by a number that is very, very tiny, you're going to get a fraction that is very, very big. And then the moment you're dividing by 0, well, you can divide by 0, so that fraction doesn't exist anymore. So those functions exist everywhere. Those exist pretty much everywhere except at a finite number of points. That's what makes those things kind of weird. Then last, you have exponential. And an exponential function is one that looks like this. This is where you have a to the bx plus c dx, or something like that. So the x is contained in the exponent. Okay. So those are pretty much the functions that we might encounter. The most likely ones are linear functions. Those are the easy ones to deal with. Of the polynomial, we're going to find some that are restricted to just like a quadratic. Can get something slightly more complicated than that, and then you might get some like those. We're going to try to stay away from those as much as possible, but I can't guarantee that that's the case. Questions? Now, many times it can be useful to graph those relationships. And so remember, if a function is just a mapping from one set to the other, and so we can put those sets in a Cartesian plane where you have all the values of x, they are all lined up here. And then for each of those values of x, you apply the function, you calculate the corresponding value of y. So for the case of the linear equation, how would that graph look like?
A line.
It's a line, and if you pick x to be 0, remember you're picking values for x, you can pick any number unless the support of this thing is restricted. And if you pick x to be 0, what is y?
B.
It's just b. So for x equal to 0, y is b. Let's suppose this is b. Great. Mark your failure day today. And what if you pick x to be 1?
It's gonna be A plus B.
A plus b. And then what about if you pick a to be 2? What is 2a plus b, right? So if you pick x to be 1, and this quantity here is a, this is going to be your b plus a. You keep doing that, for every additional value that you pick, you get one more multiple of a, and you get the equation of this line. Yeah? What about if I want to graph something more complicated than that? What if I want to graph a polynomial equation like this? How would that look like?
It's gonna be a U.
It's a parabola, right? So how do you know? Well, again, pick points, and if x is 0, so one way to say that, you put a line and then you set x equal 0, meaning that you're evaluating this thing when x is 0. So if you put it 0 in there, what do you get? You get 0 squared, which is 0. Then evaluate that at x equal 1. If you put a 1, what do you get? 1 squared is 1. If you put negative 1, what do you get? Positive 1, so you get these. And then 2, 3, 4. Eventually you will see that this thing looks like this. Clearly bad drawing, but gives the idea. Yeah? What about the rational equation? Remember there are those discontinuities? So one thing that happens with the rational equation is this. They get weird. Suppose this is a value of x such that this is 0. Then now you have some number divided by 0. So clearly this function does not exist here because you can divide by 0. But if you pick a number that is a little bit bigger than 0, then you're going to get a very large number. Any number divided by something very, very tiny, it's a large value. Do you agree with that?
Yes.
But what if you make it, instead of a little bit bigger than 0, you make it a little bit smaller than 0, so a negative number? Then perhaps the same fraction changes sign. It becomes a very large number, but negative. So proximity of the discontinuities, those graphs might look like this. Something like that. And then here, it might look like something like this. So you go from a very large positive number just by moving a little bit to the right, you now get a very large negative number. Why do we care? Well, because if you come up with a model that contains this type of expression, you need to make sure that you restrict its use away from here, because in reality, in real life, the type of applications we're going to do don't capture that. So you might have an additional restriction and say that, hey, this only works between here and here. So it's a restricted set, not here. Okay? So those are little things that you'll have to deal with. Questions? So what do you need to remember?
The types of functions.
What are functions, right? And remember that for every function there is a graphical equivalent. And all the different functions that exist, The only ones that we're gonna care about, or we're gonna see again, are the linear, polynomial, rational, and at some point, depending on how far we go, exponential. When dealing with rational functions, there are discontinuities that you have to deal with, so make sure you're aware of that. That's pretty much all you need to remember. Questions? Is it okay if I erase this garbage? Yeah. All right. So let's think about something else now. We're gonna take a little break from this. And let's think about the concept of slope. How do you compute the slope of 2 points in space?
Well, for linear, which is the assumption, is 2 points.
Well, hold on. So 2 points. Let's suppose that perhaps those are part of a line. But those 2 points can just be 2 points. I want to know the slope of the line passing through them. How do you compute that?
The change in y divided by the change in x.
So the slope is defined as the change in y divided by the change in x. Yeah? So if we give those 2 points to a set of coordinates, say this is point 2, the coordinates of this guy are x2, y2, the coordinates of this guy are x1, y1, the slope is the change in y divided by the change in x, which is, if you use point 2 as your first point, it's gonna be x2 minus y2 minus y1 divided by x2 minus x1. Do you agree with that? So it's the change in their y coordinates divided by the change in their x coordinates. I just pointed incorrectly, but that's what it is. So alternatively, you can pick the first point to be the first. So you have y1 minus y2 divided by x1 minus x2. So remember, when you're calculating the slope, the subscript must match. Okay, this is the y coordinate of one point and the x coordinate of the exact same point. Don't flip them around. So let's do an example. What is the slope of the line passing through 4, 8 and 3, 5? So when I give you 2 points, what is the first number? Is the x coordinate, the second point is the y coordinate. All right, so the slope is y2 minus y1, x2 minus x1. So your y2 is 8. I pick this to be my second point, and I pick this one to be my first point. Divided by 8 is matched with 4. 5 is matched with 3. Yep. So what do you get?
3.
3 over 1, which is 3. Do you agree with that? Questions? We good? All right. So let's extend this idea. Let's pick a point this point has coordinates 1, 2, and then let's pick a possible other point in space. Could be this one, and this point is 8 units away from the other point. and its y coordinate is 4. What is the x coordinate of that point? So if this is
X coordinate's 1 plus.
1, and this is 4, is given, what would be that?
That one's 6 for sure. Wait, I'm getting that. That's just 1 plus A.
Is this starting point plus the distance I just gave you, right? So that is 1 plus A. So this is 1 plus some quantity. Yeah? So what is the slope of those 2 points? It's a change in x. So if I can pick this to be my x1, and or my point 1, so it's 2 minus 4 divided by the coordinate, the x coordinate of this guy is 1 minus 1 plus A. Do you agree? So what is the answer here is minus 2. Here you have 1 minus 1, but then you're making a negative 2 over A, whatever that A is. Yeah? Do you agree? So what do you think is going to happen graphically? Look at the picture. If I make this A bigger or smaller.
The distance between the two is either
So if I leave A to this value, whatever this value is, the line that connects those 2 points is slope like that, right?
Mhm.
Whatever that number is. But if I make A bigger, and of course I leave the y coordinate the same, what happens to the slope? Well, instead of being this, the slope of that line, I'm dealing with the slope of this other line. So if I change the location of the 2 points, then the slope is affected, right? Do you agree with that? Yeah? What if I hold everything constant and I change the y location of that point? What is gonna happen to the slope?
Become steeper.
So if I increase the y location and hold the A constant, if I change the height of this thing, then the slope is going to change. If I make it smaller, then the slope is going to change the other way, right? So the moment I change the coordinates of the second point, the slope is going to change quite a bit. There is one specific trade-off between changing the x and changing the y that actually keeps the slope constant. And if I increase A by this much, whatever this quantity is, but then at the same time I increase y by this much, then the slope remains constant. So the only way to keep the slope constant is if you change x by, x by whatever you want, but y by a particular value that is related to the x. Questions? You're good? All right. So let's change scenario. Let's suppose that you have y that is related to x by some function. It could be linear, it could be quadratic, it could be whatever, we don't know what it is. Then, how do you find the slope at x1, or the slope between points x1 and x2? So let's think about this. This is your y, this is your x, this is your point x1, and this is your point x2. And to find the slope, you need to calculate the change in y divided by the change in x, right? So if you know that, if I give you x1, can you tell me this value of y? what is this height?
f of x1.
Well, you know that the y is related to x by means of this function, so this would be f of x1. Whatever it is, it can be a quadratic, it can be a cubic, polynomial, whatever. What about the y value of x2? Well, it's just gonna be that rule applied to x2, so it's f of x2. Yeah? So using this notation, what would be the slope connecting those 2 points? Now remember, we don't know what the function is. The function could be anything. The function, we know that passes through those 2 points. So the function could be something that looks like this. The function could be that line, or the same thing flipped around. I don't know what it is. I just know those 2 distinct points of it. So how can we find this slope?
Same old f of x2.
So just the same process as before. Look at the y coordinate of this point. So it's f of x2. Subtract the y coordinate of the other, f of x1, divided by x2 minus x1. Yeah, so we're doing the same thing. What is changing is the notation that we're using. Okay? Does it make sense? All right. So let's take this and extend it a little bit more. Let's suppose you have an actual function. What function is this? Or what is meant to be actually, because it's not quite it.
Upside down parabola.
It's a parabola, right? And so if I pick this point, and I pick this point, so if you pick this value of x1, whatever it is, you can calculate f of x1 because you know the rule. It's the equation of a parabola. If I give you the value, the x coordinate of this point, you can calculate the y value of it because you know the rule. And if I connect those 2 points, this is the slope that I get. But if instead of picking this point and that point, I pick this other point right here, you can see that the slope is totally different. Do you agree with that? So, what if I want to know the slope right, instead of 2 points, right on this point? How can I do that?
Make the line infinitely closer to each other.
Well, I can just pick 2 points that are very, very, very close to each other, right? What is the closest that 2 points can be, though?
Oh, well, if you make a limit.
You make them overlap, and you have 2 points that are identical to each other, basically. And now you're figuring out the slope of 2 identical points overlapping. So if I want to know the slope at this point, I can just use this approach and pick 2 points that are very, very, very close to each other. So this is my x1, and this one is my x2. And now the slope that connects those 2 points is just a line that is barely tangent, almost tangent to this function right here. So one way to look at the slope at one point is to pick 2 points that are very, very close to each other. The way we do it, slope of a line at one point. The way we do it is pick 1 point. Let's call this x0. Then pick another point. Very close to it. So what I mean by very close? Well, it could be this value that you picked plus a bit. Let's call it h. Yeah? And then compute the slope. So what do you get if you want to do that?
You would get.
So essentially you have 2 points. You have x0, and this x0 is connected to the y value that is calculated by using that formula applied to x0. And then you have this x0 plus h that gives you a f of x0 plus h. Yeah? Then if I want to compute the slope at the point, this is my first point. This is my second point. Divided by your x0 minus that. So this is the same as if you do a bit of algebra, f of x0 plus h minus f of x0 divided by h. It is always going to be like that. So let's see if this can make sense in a minute. I'm gonna have to go to the back. Sorry, guys. So compute the slope of dx plus 1 at x equals 2. Okay, so I'm asking you to compute the slope of what kind of equation?
Linear.
It's a linear equation. Can you tell me what the slope is without doing any math? The slope is 3, and this is the intercept, right?
Mhm.
So the slope is 3. You know that the answer is supposed to be 3. Let's see if using the logic, that approach gives us to that answer. So your first point, your x0 is 2. Now pick, evaluate the function at 2. What do you get? 3 times 2 plus 1, 7. Yeah? Now pick a point next to it. The next point is going to be 2 plus that bit. Evaluate the function at 2 plus a bit. And what do you get? Well, you get 3 times 2 plus a bit plus 1, which is 6 plus 1, 7, plus 3 times that. Yeah? Alright, so now compute the slope. If this is my second point, 7 plus 3h. So this is my y of 0.2 minus y of 0.1 divided by x of 0.2 minus x of 0.1. Yeah? So let's clarify here. This is my y2, this is my y1, this is my x1, this is my x2. Yeah, so I did the exact same thing that we did there. Now, of course, things are more messy. Now, fortunately, things cancel each other out. So 7 minus 7 is nothing, so you get 3 times h divided by 2 and minus 2 cancel each other out. What do you get?
3.
You just get 3. Yeah? So clearly this is a trivial example because we already know what the answer was, but served us to use this approach and verify that with a known function we get the correct answer. Yeah? So what this is telling us is that it doesn't matter how far those 2 points are, the 2 points that you pick. The distance between the 2 points is h. It doesn't matter how far apart they are. The slope between them is always gonna be 3. Doesn't matter where you pick any of these 2 points. But this is not always the case. If you take the scenario right there with the parabola, if I pick a point and another one that is far away, I get a slope. If I pick the same point and one other point that is a bit closer, the slope is going to be different. The only way to get the slope at a point, I would have to pick those 2 points very, very close to each other. So let's try it with a parabola. Slope of a point on a parabola. So let's pick this function right here. It's the easiest parabola. And let's pick a point. Let's pick one because it's easy. And so what is the f of x?
1.
F of x0 will be x0 squared, which is x0 squared, but then evaluate that at x is equal to 1, you get 1. Yep. So then pick another point. You get that. And now things go weird. F of 0 plus h, which is equal to f of x of 1 plus h, which is equal to 1 plus h squared. What do you get? Square of a binomial, it is the first number squared
Plus 2.
plus twice the product of the two plus the last number squared. Yeah? Algebra is awesome. If you don't believe me, then well, figure it out. So distributive property, this guy times that guy is 1. This guy times that guy is 1h. This guy times this guy is h. This guy times this guy is h squared. Yep? So there it is. Alright, so now let's use our slope formula. My first x, my first y is y1 minus y2, x1 minus x2. So this is my y1 is 1, my x1 is 1, then I have my y2 is this quantity here. And this is my x2. Yep. So just drop the parentheses and change the signs. You have 1 minus, so this is all the stuff in front of the parentheses, I change sign of it. You get minus 1 minus 2h minus h squared. And on the bottom you have 1 minus 1 minus h. So just distributed the negative throughout. So 1 minus 1 cancel each other out, and minus 2h minus h squared. 1 and 1 cancel each other out, minus h. Yeah? So now you can factor and simplify. So you have minus h that multiplies 2 minus h. 2 plus h, you factor out the negative, divided by minus h. Cancel each other out. Look at that. Yeah? Do you agree with that? So what is the slope of this point of a parabola? Well, this is how it's in graph. The slope at x equal 1. If I pick h to be this much, the slope of this line is going to be 2 plus whatever distance you pick. Yeah. What if I pick h to be negative? Or something weird is going to happen. What if I pick h to be exactly that much? So that my next point is this one.
The negative.
What will be the slope?
Negative 2.
If I pick it just enough, the slope would actually be
0.
0.
Yep.
Yeah.
Oh,
If I pick this point right here. Do you agree with that? But which measurement of slope is better? By picking this point, or one that is right on top of x equal 1?
on top. The closest.
The closest you are, right? So what is the closest two points can be? Well, if they overlap, the distance between them is
0.
0. So if I make this approach 0, what happens? Well, the slope is
2.
2. Okay, so ultimately, when we're looking at the slope of a line, the slope of a function at any point, we just want to pick the 2 points that are adjacent but overlapping, and that's the most precise way you can measure that slope. Questions? What time is it?
2:01.
2:01?
I think that clock works.
Oh, it does?
Oh, it does.
It's an odd sight. Yeah.
Yeah.
I was a little surprised when I saw it actually having the right time.
That's,
last
it's
class
an
clock
it's an innovation we did in.
Actually, no, it's like 10 minutes ahead.
It's not what?
What? Is it? Am I wrong?
It's two
Oh, never mind,
2:02
never mind.
right there, man.
Mine-
You-
mine's
can you read the
wrong.
clock?
Confused now. That's not close. So, have you seen this stuff before?
Yes.
Yeah.
How long ago?
Middle school.
Been a
So,
second.
5 years ago.
Yeah, I was saying
in
second.
high school, and then this stuff maybe in high school.
Yeah.
Sophomore year.
Unfortunately,
Sophomore.
many universities have moved
Really?
away from teaching
This is
calculus to
algebra?
their college and business
When was
students.
the last time I saw it?
And
I did freshman.
many others have gone back to include calculus to their program. When you go in the workforce, you apply for a job, you're gonna be compared against somebody who has taken calculus, and if you're doing financial economics, you better know it. Yeah, there must be disadvantage, not your fault. The way, some of my colleagues push for the curriculum changes has been to remove calculus, and, in the long run, that would be detrimental for you, but just because you were not exposed to it does not necessarily mean that you don't have to know it, right? Just, those are the essential things, review it, and eventually you'll learn how to use it. It's true, most likely, 10 years down the road, I don't think your employer is gonna come and ask, hey, what is the derivative of, whatever, who cares? But you need to know the concept, and so this is the part that, we need to extract from this. Of course, for academic purposes, I will give you, if we do it, then you're responsible for knowing it. You're gonna get some questions in a quiz. You're gonna practice those things. But what I want you to retain is the idea of how do those slopes work? And why do we care? I mean, the reason why we're gonna care about this is because eventually, this is where we're heading. I have some function, I don't know what that function is gonna look like, but the one that matters to us is the weight of an investment, so how much you invest in that asset in your portfolio. And perhaps portfolio risk. Mathematically, we're gonna develop a relationship, how by changing your asset allocation, how is your risk exposure going to be? Well, let's suppose that it's like this. Do you want risk to be high or low?
So,
You want it to be low. So if you have to pick, if you have to pick a specific weight, and you want to be exposed to the least risk possible, which weight would you pick?
The rate of change is 0.
Let's see where this is the lowest, right? So lowest risk. So the lowest risk is gonna be this amount. I don't know what the number is, but I know that the way I obtain it is by picking this particular weight. Does it make sense? So how can I actually figure out what is the weight of my asset allocation that minimizes my overall risk? But if I know the mathematics of it and I want to find the smallest point of this graph, what is particular about the smallest point?
The rate of change is 0.
Well, if you draw a line, and you would see that the line passing through the smallest point, the slope of the line is 0. So that's one thing that we're gonna figure out is, hey, look, when slope is 0, that means that you have either a minimum or a max. So in this particular case, I'm interested in the minimum, right? I want to have the smallest risk. So if I can find a way to figure out the slope and then find where the slope is 0, I can figure out where I should put my money to minimize risk. Conversely, we can do the same thing for, instead of risk, we can look at Sharpe ratio. The mathematical function is essentially a rational function. In this case, it's complicated, but the Sharpe ratio looks at, scales down the risk that you have for the returns. Scales down the returns of a portfolio by its risk. So it's a ratio between returns per unit risk. How do you want this ratio to be, high or low?
You want your returns to be high.
You want returns to be high for 1 unit of risk. So
Ratio high.
that curve kind of looks like this. So where would you like to invest your money in this case?
At the
I
max.
want the highest possible point, so find where the slope is 0. And the value of x that gives you the slope of 0 is the asset allocation that gives you the best trade-off between returns and risk. So this is the reason why we're doing all this stuff, because we want to figure out how should I put my money so that I either get, I don't know, lowest risk, highest returns, best trade-off between returns and risk. Okay? Questions? So what we're gonna do next time is continue this discussion. We're gonna mess with slopes a little bit more, and eventually we're gonna figure out that to finding the slope of a function at any point in time is called taking a derivative, and you can take a derivative using this method. Pick a point and then one next to it, and then shrink those 2 points so that h becomes progressively smaller and smaller and smaller to the point where it becomes 0. But doing things this way is kind of time consuming. The alternative is to have somebody figure out this stuff for different types of functions and come up with a set of rules. So for instance, if you have this function right here, you can find an equation of the slope at any point by applying this rule for derivatives, and you will see that if you take the derivative of this, what do you get?
6x plus
6x plus 1. So essentially I did all this work applied to that in my head, just because I know the rules. So the idea of derivative is to skip all those steps. But the point is that you're finding an equation that describes how the slope changes along the stem. Okay? So that's what we're gonna get to. It's not complicated, it looks fancy and pretty, but we're only gonna cover the derivative rules that apply to us for the functions we're gonna do, and it's not that many. How many of you have not taken the derivative, by the way? One, two, three. Anybody else? Have you ever seen this stuff before? So it's not that bad. It's the concept is probably the hardest part, and the application of it, once you know the rules, it's pretty simple.
Basically, this is calculus.
I should have took it.
All right.
Huh?
So I should have took it.
What is it?
I took it, but it was 4 years ago.
The only thing I did was pre-cal. That only just kind of like glanced over it.
Yeah, no, pre-cal. Believe me when I say it. Pre-cal is nothing like calculus.
Yeah, I know it's not.